Today we're going to be talking about limits, which is a fairly abstract concept, so I'm going to motivate it first with an example. And this example you should all be familiar with because it's about velocity. So it's time Let's track your distance from home when you leave in the morning for school. Okay, that's just some idea here. You've stopped, and here you're going faster, etc. Now, suppose you wanted to know your speed between these 2 points, and let's just say t equals 1 and t equals 4 here. You know how to compute average velocity. That is the distance over time, right? So here's the distance. Let's say y1, y2 over time, x1, x2. So average velocity equals rise over run. Now let's ask another question. How about if you wanted to know your speed at exactly this moment, exactly this point in time? Here's x star, all right? Then we don't have a rise over run, right? There's no change in y at this very instant. There's no change in x. Okay. However, what we can do is make these average velocities over a smaller and smaller period of time so that my x1 and x2 here get smaller and smaller. So I could take an average velocity over this interval, my x1 and x2, or over this interval, smaller and smaller intervals. What's happening to the denominator as I take the average velocity over smaller and smaller intervals? This quantity is going to 0, right? And in fact, this quantity between the differences from y1 and y2, that's also going to 0. So that is a problem, potentially, right, because of the big issue in math, which is the fact that you cannot divide by 0, okay? So that's just a little bit of motivation behind why we're interested in limits. We're interested in something called instantaneous velocity, but that involves this denominator going to 0. And we have to understand, make this idea very precise. What do I mean going to 0? At what rate? Or what does it even mean to be instantaneous? Okay? So we'll start with a very simple example. Let's look at this function f of x equals x over x. Now you might think, well, that just equals 1. You can cancel the x's. But that's not always true. When you plug in 0 for x, f of 0 equals 0 over 0, which is undefined. So 0 over 0 is undefined. So this function equals 1 when x is not equal to 0, and it equals undefined when x equals to 0. We could, for example, fill that hole by defining f of x as x over x for x not equal to 0, and 1 for x equals 0. That graph would look like this. Or we could define x at 0 to be another value, let's say 2. And that graph would look like this. Now, suppose you want to find the instantaneous velocity function like that. Let's just say this is x squared. It continues on the other side, but we won't be interested in that. And I want to find the instantaneous velocity at 1. What we can do is find a value close to 1, and again do the average velocity. So what's the rise? The rise is x squared minus 1, and what's the run? X minus 1. And the idea is that we want x to get close to 1. And that means x squared is also getting close to 1 in the numerator. So what we want is the limit as x goes to 1 of x squared minus 1 over x minus 1. And why are we interested in the limit? It's because at 1, just like at the problem before, x over x, the denominator is 0. So we cannot actually just plug 1 in. We have to use this concept of a limit. But we can do some algebra on this, right? This is the limit as x goes to 1 of x plus 1, x minus 1 over x minus 1. And since we're just taking the limit, x is never going to equal 1, because the limit means that you're getting very close to the point, but you're not actually arriving at that point. And so I can cancel this out. If it were 0 over 0, I wouldn't be able to do this, but x will never be 1 because we're taking the limit. And so we just have limit as x goes to 1 of x plus 1, which equals 2. It's important to note that limits don't always exist. And a very simple example would be the function f of x equals 1 of x. What does that function look like? As x goes to infinity, 1 over x gets very small. And as x gets very small, 1 over x goes to infinity. And if we replace x by negative x, we get negative f, and that's why you can reflect about this line. Okay, so here's a function, and it's clear if you understand what the graph looks like that the limit as x goes to infinity of f equals 0. So you can see as x approaches 0 from the right that the limit is infinity, and then as x approaches 0 from the left, the limit is negative infinity. And then the limit as x goes to negative infinity of f of x is also 0. So an understanding of the graph of the function really gives you a very good sense of what's happening at critical points. In this case, it is 0, since the function is undefined at that point. So this is what's called a vertical asymptote. And this is a horizontal asymptote. This is a quintessential example of a limit that doesn't exist. So this is the quintessential. So this is the quintessential example of a function that is going to negative infinity or infinity. In this case, both do not exist. Both limits do not exist from the right and from the left of 0.